Good evening, ladies and gentlemen. Welcome to our third and final Mercury Transit Google Hangout. I have again two special guests with me tonight. First of all, Professor David Rothery he's a professor of planetary geosciences at the Open University. He has many years of experience working on planetary geology, focusing on Mercury, so he's probably the planetologist specialist for this evening. Joining us as well is Remco Timmermans from the International Space University. He serves there as a faculty member, but that's only one hat he's carrying. Actually, he's with us today not only because of his faculty membership with the International Space University, but because he had a very special week behind him with some very unusual experiences. A lot of Europeans, including myself, have been envying a lot. So Remco and David, very welcome to this Mercury Transit Hangout again. Well, to start with, for those of you who did not have a chance or were blocked by, I don't know, clouds above their local skies, last Monday, starting at just after 1 o'clock in the afternoon, we had a not super rare but not so often happening astronomical event when Mercury transited over several hours over the solar disk, an event which is happening almost a little bit more than once in a decade throughout the ages. Predicted about like 400 years ago for the first time by Johannes Kepler, who didn't live to see it. However, this time it was spectacular in a way because not only a lot of ground-based operations were taking place, but also space-based operations. And because of the timing of the transit, we had the chance to see both in Europe as well as, for example, South America. And Remco, that's exactly where you were going. So, Remco, let us know, how was it there in Chile when you were visiting the European Southern Observatory?
Yeah, well, thank you, Gernot. Yeah, obviously, going to Chile to watch the European Southern Observatory installations is very awesome by itself. But the fact that we were there exactly during the Mercury transit made it just a little bit more special, even. And what I'd like to do, if that's okay with you, is just show you a few impressions of our experiences in Chile. I prepared a very short presentation just to give you an idea of what we did and how the Mercury transit was part of our experience. So let me just go there right now. Share here, and you should be able to see our group. So a group of 8 social media influencers were selected by ESO, and there's 2 ESO press officers here with us to travel to 2 different locations in Chile, where the European Southern Observatory has its installations. This is at the Very Large Telescope. Unfortunately, ESO, it's a great institute. They're not very creative with names. The Very Large Telescope, they just call them the VLTs in Paranal. And this is the location where we were during the Mercury transit. And let me just take you through the view of the 4 8.2 meter telescopes that they have there, which is kind of the main part of the installation there. Now, obviously, the 8.2 meter mirror telescopes are not suitable at all to be pointed to the sun. So we watched the Mercury transit last Monday through 2 different telescopes, much smaller than the ones on the mountain, but very interesting. The European Space Agency was doing a parallax experiment, watching the Mercury transit from 2 different locations on Earth. One in Paranal in Chile, which I'm pointing to right now, 2 relatively small solar scopes, both measuring or looking at the sun in different wavelengths. That was connected to a similar or the same setup at the ESA at the site in Tenerife. From where they connected the 2 images for a parallax experiment, which they call CESAR, and you can look at the ESA CESAR website to see exactly what that meant. This is the instrument looking at the sun itself, and this is in a cardboard box the computer that they use to transit or to receive and transfer the images online. This was live broadcasted online. Both from Paranal, one of the images that you see vaguely in this screen, and the same image from the Canary Islands. Very interesting to see this.
Was that am I right if I saw a Coronado telescope in the first slides? We have an H alpha filter, or
Yes, they had an H alpha filter on the one, and the other one I don't remember exactly. I mean, you may know more about this than I do, but yes, one was definitely in the H alpha, and the other one had a different filter on it. And what exactly it was, again, look it up on the website. But they were looking at it in different wavelengths. The other setup was probably much more similar to the setups that we saw in many places in Europe, because I followed the Mercury Transit hashtag on that day, and we saw pictures of setups on the streets at different institutes, basically all over the world where the transit was visible. Very similar to this one. This is what they call the UT5, so the VLTs are called UT1 through UT4, and kind of jokingly, they call this this amateur telescope setup, they call it UT5. This is where the astronomers in Paranal do their own personal observation just for fun during the night, but also during the day using a solar filter. They were following the Mercury transit through this particular telescope, and they broadcasted it, interestingly, to different monitors that were displayed on site for the astronomers that were not necessarily at work at that moment, in the canteen and in the lobby of the residence. We could follow the Mercury transit on a live video feed from this particular camera right here.
Remco, I think it's very important for our viewers to know that given the daily life cycle of astronomers working in Paranal or also La Silla, having something in the morning means actually in the middle of the night for the astronomers. So I guess that most of the actual astronomers working on the big telescopes were already in bed or sleeping already when you did those observations, I presume.
Well, not necessarily, because they have astronomers that do the observations. Obviously, the optical observation are only done during the night, but during the day, the observations for the next night are prepared, and the observations of the previous night are being analyzed. So they have a set of astronomers that work during the day, that work on the data of the previous and preparing the next night. So no, it's not the case that all the astronomers are sleeping during the day necessarily. So they work in shifts, like many 24-hour operations do, because it really is a 24-hour operation, although the observations are only done during the night. Mm-hmm. So this is the little setup that we watched the Mercury transit in. Obviously, Europlanet Media encouraged people to use this hashtag, the Mercury Transit Selfie. So Jane MacArthur, who was in the second Hangout with you 2 weeks ago, and myself, we felt obliged, of course, to do a Mercury Transit selfie while we were together watching the Mercury Transit through the UT5 telescope. And I saw that many other people did. We also visited the site. There's this flat mountaintop that wasn't flat a few years ago, but this is the location where the extremely large telescope, the EELT, the European Extremely Large Telescope, will be built. Actually, the building preparations have started, and it should be ready, I believe, in 2026. We should have a 32-meter telescope on top of this 3,000-meter mountain. Way too early to watch the Mercury transit from there this year, but this was on the same day, of course. We did, however, that was very interesting. We visited, a few days later, we visited the Atacama Large Millimeter Array, the ALMA array, 66 radio telescopes at 5,000 meters under pretty harsh conditions that day. So although it's the driest place on Earth in the Atacama Desert, we experienced it in blizzard conditions, the feeling temperature with hard winds about minus 20 degrees. And mind you, this is 25 kilometers from one of the driest deserts in the world. Pretty tough conditions, but through these telescopes, and this picture I took during one of the lulls in the blizzard, with all the telescopes set in safe position, so there were no observations being done at that moment. But interestingly, during the Mercury transit, the people at ALMA, they used one or two, I don't even know how many telescopes, sort of experimentally, to use radio astronomy to watch the Mercury transit. And they will send out a press release about this soon, but they compared their picture on the right-hand side using band 7, the 345 gigahertz band, to a picture taken by the SDO satellite at the exact same moment of the Mercury transit. So even radio astronomy and radio dishes can be used to watch these types of phenomena. So let me go back to myself again. How do we do that? Yep, there I am again. So that, in a nutshell, was a bit of the adventure that we had. Now, obviously, the purpose of our trip to Chile, the Meet ESO trip, was not entirely for the Mercury transit. There was a lot more. It was a big outreach education event via social media, which, to my opinion, was quite successful. But the Mercury transit was an important element of it, and I'm really honored to have witnessed this very rare event at that very special place.
I'm sure it was both an adventure and a very deep insight into European astronomy and European space exploration. So again, I really envy you. I was there many years ago, so I have to ask you a personal question. Do they still have free ice cream for the astronomers?
Oh boy, yes they do.
Okay.
One of the big perks of working there is good coffee, good ice cream, and yeah, they take care of their astronomers. So absolutely, free ice cream. That's one of the first things we learned after we arrived. So it's totally there.
I went to the Atacama as a geologist 20 or 30 years ago, and I can tell you there was no free ice cream at all for the geologists.
Sorry about that.
Sorry, David. Okay, but having seen the radar telescopes there is actually for me a little bit of a lead-in into my next part of questions, and that is obviously you wouldn't use something like the VLT for Mercury observation anyway, of course, but you could use the radar telescope. So when you point a radar telescope to Mercury, not just measure the passive emission, but also do a radar bounce, you not only can measure the distance to Mercury, but as radar waves have the property of sneaking a little bit around the corner depending on the wavelength, also the polar region of Mercury, which, as we know, is so close to the Sun, it's a scorching hot surface if you go to the subsolar point. However, in the polar regions, you find something there with the radar waves which should not be there. David, am I wrong here?
Well, you're referring to the craters near the poles whose floors never see sunlight. Mercury's spin axis is not tilted at all. It's 90 degrees to its axis, almost not 90 degrees to its orbit. So there's no sunlight that gets to the floor of the craters near the poles. So the temperature there is permanently minus 200 and something centigrade. It's very cold, and water ice has collected in those craters. We thought this was the case on the basis of radar observations made from the Earth, which showed something very reflective in these polar craters. It could have been sulfur. Now we've had a spacecraft, the NASA messenger craft, in orbit around the planet. We're convinced that it is, in fact, water ice that's in the polar craters. And this occurs on the Moon as well. The Moon has polar craters with water ice inside the permanent shadows. And the delivery mechanism is whenever a comet hits the planet's surface or the Moon's surface, the cometary material is vaporized, and those water molecules, some escape to space, others just bounce around as individual molecules. And if the molecule bounces and lands on a hot surface, it will bounce again and keep bouncing. If it lands on a cold surface, it will stick there. If that cold surface is just cold because it's night, it will stay there till the sun rises. Then it will float away and carry on bouncing around until it escapes to space. But if it lands in a shadow which is permanent, it will stay there forever. And over millions of years, it will be joined by other water molecules until you build up a layer that can be several meters thick of ice. And this is there in the polar craters on Mercury, just as it is on the polar craters on the Moon. So very strange to have somewhere on the closest planet to the Sun where it is extremely cold and there's plenty of ice.
So it is a planet of contrasts, obviously, and interesting that you mentioned the Moon as well, because if you look at an old image of the early space probes which were flown to Mercury and then compare it with a amateur telescope picture of the Moon, at the first glance they look very similar. You have this grayish coloring. You even have the crescents because of the illumination angle at the time when the first pictures were taken at Mercury. You see craters, you see impact basins, you need shattered areas. You really have to be looking very close to it to realize, oh, this is not the Moon, but this is Mercury. Since then, obviously, our understanding of the Mercury has evolved tremendously, but it's certainly not really that we have all puzzles solved. So, David, if I may dive right into it, what would you say are the main scientific lead questions we have nowadays about Mercury?
Okay, you're right. At first glance, Mercury can look like the Moon. It's airless, it's heavily cratered in some places. But if you look at Mercury, you don't see some areas that are darker and some areas that are more reflective. Look at our Moon. The lunar highlands are quite pale. The lunar maria, the areas flooded by lavas, are much darker in comparison. You don't see that contrast on Mercury. And the reason is that Mercury is almost entirely flooded by lava, so it's the same dark tone everywhere. But there are some areas which are older and are more heavily cratered, and some areas that have been flooded by lava more recently, but still mostly more than 3 billion years ago, which are smoother and have fewer craters. So at first sight, it's very Moon-like. In detail, there are many differences, and the differences include the composition of the lavas. They're very high in magnesium and low in iron, and this is telling us that when Mercury was molten, the magma ocean surrounding Mercury, from which the first crust formed, was poor in iron, and therefore it had a low density, and not many crystals were able to float. The Moon once had a magma ocean, but when that was cooling down, it had enough iron that the magma ocean was sufficiently dense that reflective crystals, the mineral called anorthite, it's a kind of plagioclase mineral, could float to the surface, and that's what's formed the lunar highlands. That could not happen on Mercury, we now know. It was so poor in iron that any anorthite, any plagioclase crystals would sink to the bottom. And the only thing that would float is probably graphite, the mineral form of carbon. And we think possibly the first solid crust on Mercury's magma ocean was made of graphite, so a carbon crust. This comes out as a result of modelling based on the messenger determinations of the iron deficiency in Mercury's crust. And just at the very end of the Messenger mission, just over a year ago now, before Messenger hit the surface, they got measurements from the neutron spectrometer suggesting a richness in carbon in certain dark blue coloured areas of Mercury's crust. So when we get there with our own European mission in 2025 called Bepi Colombo, we will be looking very hard to prove that these traces of surviving earliest crust do have plenty of carbon in them. Another big surprise about Mercury, and this was not suspected before Messenger got there, is that it's generally rich in volatiles. Now you can call carbon a volatile element, but also there's sulfur. Everywhere you look on the surface, there's 2 to 4% sulfur. That was a big surprise on a planet that close to the sun. You'd expect sulfur to have been driven away by heat-related processes when Mercury was forming. It's also rich in chlorine and in potassium and some element or some substance which turns to gas, because the most recent volcanic activity is explosive. You can see craters that have been blasted up through the surface that aren't impact craters, but explosions driven from below by violent explosive eruptions. So the magma rising upwards must have some gas dissolved in it, which comes out of solution explosively and jets the fragmented rock into space. And we can see the deposits of stuff that's fallen out from these eruption plumes around the vents. So there's something sufficiently volatile in sufficient abundance to drive explosive volcanic eruptions. And who'd have thought that so close to the sun? And then there's the hollows, a class of feature which we couldn't detect until we got into orbit. Areas where the top 10 or 20 meters of Mercury's surface has just been stripped away. You've got steep-sided, flat-bottomed depressions, hundreds of meters to kilometers across, but when they merge together. And the top layer is just going. It's something that's turning straight to vapor now. It could be the heat of the sun, it could be micrometeorites or ultraviolet light breaking bonds, but whatever, it's something that's volatile and just goes away. So we're dealing with a volatile rich planet really close to the sun, and that doesn't stack up. We're beginning to wonder, well, where did Mercury form? Does it belong where we now see it? So it's a big fundamental question to answer. Why is Mercury like this, and yet it's so close to the sun?
do we have any idea about how recent the volcanism happened on Mercury? Like on Mars, we know there's still some residual activity. We have some indication of residual lava flows, some old heat pockets from radioactive decay. Do we have something similar at Mercury, or do we say, well, those volcanoes, they exploded a long time ago, billions of years ago, or is this more recent activity?
Okay, Mercury probably more or less turned off longer ago than Mars did. We're not quite sure. I'll tell you what. There are very extensive areas flooded by lavas 4 billion years ago, and they're now heavily cratered. The stuff that was flooded by lavas 3.7 billion years ago happened after most of the cratering, so it's much smoother. There are some smaller areas who are flooded by lava with slightly fewer impact craters superimposed per unit area, which seem to be younger. But the big areas, hundreds of kilometers across, flooded by lava, mostly are older than 3 billion years. Now, the planets are 4.5 billion years. But there are some smaller areas, about 100 kilometers across, flooded by what looks to be lava. It could be impact melt from the impact that produced the crater. We think in some cases it's definitely lava, which are younger than 3 billion years. Very hard to put a date on it because the areas are too small for reliable crater counting statistics.
Yeah.
But there's also the explosive volcanism, as I mentioned, where you can see explosions from below the surface that haven't emitted lava that's flowed across the surface, but ash that's gone into the sky and fallen back. And the youngest such explosive events are punching through the terracing inside impact craters, which look to be young impact craters. There's at least one example of an impact crater which seems to be less than 1 billion years old, which has a volcanic vent punching through it. So if the impact crater is less than 1 billion years, the volcanic vent that's punched through it has to be even younger than that. So some volcanism in the past billion years. Not a lot, but some.
Some Lone Ranger volcanoes surviving and mostly explosive past a long time ago, I guess. So, yeah. So obviously, there is a lot of debates going on particular surface features on Mercury, and I'm aware of the same type of discussions we have in the planetology community, that we have something which looks strange. You don't go in for the eureka moment, but it starts with, oh, there's something strange we haven't seen anywhere else, and then this debate starts, and you do the modeling, and you have the people who have a lot of experience arguing for the one explanation, and then you have a counter paper just a couple of years afterwards or so. So that actually means that we are, in discussion phase, and the only way I see to settle this is actually get our feet down on the ground as much as we can, and that translates into sending a probe there. And as I said just a year ago, Messenger crashed into Mercury, and we have something beautiful coming up, a big mission, big European mission, lighting up our view of the solar system of Mercury in the form of the David-Colombo mission by 2025, arriving here at the planet. Now, you've tackled a few of those questions, David. Thank you. And David-Colombo is actually set out to attack some of those questions with appropriate measurements. So Can you enlighten a little bit about what kind of instrumentations we're looking into? And I must say, David-Colombo is a pretty versatile instrument. It's actually it's two missions in one. Can you say that?
Yes, it is. And it was designed before the Messenger mission produced its results. And I've just come back from a meeting in Madrid where we were reassessing what we need to do. We've got the right suite of instruments, but the goals of the mission have changed because Messenger has thrown up new questions for us. So there's the Japanese orbiter that's run by JAXA, the Japanese Space Agency. That will have an eccentric orbit and will be studying the magnetic and electric fields around the planet and looking at some of the particles around the planet. And then there's a probe in a much more circular orbit that's owned and run by ESA, the European Space Agency, which will study both hemispheres of the planet equally well. But NASA's Messenger mission was in an orbit which was low over the northern hemisphere, but a long way away from the planet over the southern hemisphere. It was a strategy to avoid the probe overheating. Bepi Colombo will do both hemispheres equally well with a new suite of instruments. I mean, there's an X-ray spectrometer which will give us the elemental abundance on the surface with a spatial resolution of a few tens of kilometers. This is using the sun to shine on the surface. The sun's X-rays hit the surface, and Mercury's surface fluoresces back with energies of very specific energies. And by analysing the energies of the X-rays we receive, we work out what elements are there and in what abundance. So we'll do that very well. There's a thermal infrared imager, and that's never been flown to Mercury. This is an instrument called Mertis. It's a German-led instrument, and that will give us not just the temperature distribution across Mercury, which of course is of interest, but the nature of the thermal infrared emissions will tell us what minerals are present. So we begin to get a handle on the composition. So put the X-ray spectrometer and the thermal infrared imaging spectrometer together, we get a better view of the composition. We've got an Italian-led camera system, which includes visible wavelength spectrometers. That will give us detailed maps of the surface and its composition. We've got a Swiss-led laser altimeter, which shine lasers down, and they come with time delay between the laser pulse and the reflected signal. That gives us the topography. We're studying the gravity field very precisely. And we're studying the magnetic field in great detail, both the European orbiter and the Japanese orbiter. The magnetic field's very important. It tells us the outer core of Mercury must be fluid. It's no good just to have an iron core. An iron core, if it's solid, is going to be too hot to act as a magnet. You have to have an electrical conductor that's fluid and is churning around to act like a dynamo. We want to study this magnetic field to tell us quite how it's operating and to see how stable it is, because the magnetic field is what protects the surface most of the time, but not all the time, from the solar wind, which are these charged particles from the sun that hit the surface, break chemical bonds, cause these hollows to form, cause space weathering, and cause atoms to be lost from the planet's surface, because the planet is surrounded by very low density clouds of sodium and magnesium and potassium. There's hydrogen and the helium as well from the solar wind, but the heavier elements we think have come out of the surface. So it's a very rich and complex environment, and I'm really glad we have a very good double probe about to go into orbit. 2025 we'll be doing science in orbit. Maybe the next stage is to send a lander, but certainly the right thing to do next is this big, complicated Bepi Colombo mission.
Get some context about the surface. I can't wait to see the first elevation maps, and I'm sure we're gonna have Google Maps for Mercury as well, just like we have for the Moon and for Mars as well, I guess. And
anybody listening, if you look for Mercury Quick Map, it's just like Lunar Quick Map, but search Quick Map for Mercury. There's a pretty good interactive map of Mercury, including topography from Messenger that's there already. We will improve on that with Bepi Colombo. If you want to have fun exploring Mercury, go to Mercury Quick Map now.
If you want to see one of the most exciting places on Mercury as well, if you have those maps, look out for the Colores Basin and just imagine going rock climbing there, I would say, no?
The Colores Basin is a big impact. It's got a high rim.
David, I think we could go on for a long time, but unfortunately we're somewhat coming to an end of this discussion here, and I can only invite our viewers to have a detailed look at this planet, and if you have never worked with Mercury before, start a simple Wikipedia page and then dive into it. It's a world which is much more exciting the closer you look, like with any other planet in the solar system. And that is, by the way, exactly what Europlanet does. So for all of you who don't know about Europlanet, it's a Europlanet 2020 research infrastructure. It's an almost 10 million project funded by the European Commission under the Horizon 2020 program. And the project launched just last year and will run until August 2019, I believe. And it's a large consortium of the leading planetology institutions all across Europe, and there's a lot more to come. We're just starting the project, and I'm sure there's a lot of science to be gained from this tremendous network. Now, to come somewhat to the closing, and having seen all those marvelous images of Remco stepping in a almost Mars-like environment, I have to say, Here's how I observed from the backyard of our spacesuit laboratory of the Austrian Space Forum the Mercury transit. I proudly present a spectacular, complicated machine, which is called a solar scope. If you haven't seen this before, it's actually a tool for school classes. Can be bought for a couple of thousands of euros actually online as well. It's a simple projection screen. Actually, I think I have to switch on the camera here so that you can see what I'm showing you. Okay, again, here it is, the solar scope. It's basically a simple cardboard thingy with a little optical tube and a reflective mirror down here, which is focused in the sunlight and projects back to this whitish part here where you can see the sun, the screen of the sun. Actually, you could also see a Mercury transit. Actually, we did see Mercury as this tiny little dot, and I remembered when I showed some people on the street, actually, we did a little street signs showing people the planet, and their first reaction was, "Well, yeah, that's so tiny." I mean, it's this little dot, and it's, I think, although you can't do so much science with this instrument, but what you can learn in a very intuitive way is how small the planets are versus a big central star. That's all about what paleontology is as well. And that is giving us a kind of a framework, a context of who we are and where we live in the cosmos. And I find it always fascinating that you have, on the one hand, this top-notch, high-end satellites like a Solar Dynamics Observatory or instruments at the Panorama Desert on the one hand, and this visceral experience of having this little tiny planet seen on a simple cardboard projected, giving this some sense of scale. And this is one of those things that fascinates me about planetology. They can actually almost get this feeling of standing on the surface of another world and yeah, seeing what's happening. And I was not the only one, obviously. There were observations all across Europe. There were activities in all, a lot of schools on the street and universities. And I think this reinvigoration of an interest in the science really is a very encouraging phenomenon I'm witnessing from my end of the spectrum, so to say. So, Remco and David, thank you very much for your time in this enlightening third Mercury Transit Google Hangout. It's the last in this series, but there will be more shows coming up in the near future, because Europlanet has been opening a lot of field sites and laboratory facilities to researchers across Europe. And depending on which university, which laboratory, and which group, we will be offering those live links. Actually, the project name Field Connect within Europlanet, and I'm very much looking forward to see you then again. Remco, David, thank you very much.
You're welcome.
Ladies and gentlemen, everybody watching this Google Hangout, thanks for watching and staying with us. My name is Gernot Groemer. I'm with Europlanet and the Austrian Space Forum. Good evening.